Hello, my friends. This is Dr. Mohamed Nezami with another lecture on RF and microwave circuits and systems, with emphasis on modeling using CAD tools. I have been talking about the use of Pathwave SystemVue for baseband and RF system simulations, and we have been doing so far we have two videos on the system design. One was an Inmarsat front-end transceiver. Another one was a KU band block down converter. Both you can check the playlist and watch those if you like. Now today, I'm going to cover another concept, which basically is the concept, since we've covered the KU band low noise block down converter. Okay, we are going to go to the other side, to the transmitter side, and talk about as an example, a 10-watt SATCOM block up converter with GaN, that's gallium nitride power amplifier, or GaN on silicon. Now, as you are aware, GaN power amplifier devices have been revolutionizing the communication hardware industry for microwaves and RF. These are very high density power devices. And now they are overwhelmingly outpacing all of the use of gas devices for high power amplification. Okay, so today's example is just an example. So like I said last time, we have covered the use of LMB. This is an assembly, a feed assembly for a VSAT terminal, SATCOM terminal, where we have here's the horn. We have a parabola usually sits in here, and this horn is at the focal point or at an offset. We have an OMT here, okay, that splits the transmit or receive. And on the receive side, we have a transmit rejection filter to reject the BUC high power signal that goes out from leaking out here to the LMB. So we have covered in the last video a typical design of this KU band low noise block down converter, where we take KU band signals in the receive band, a block of them, and move them down to an IF signal that we could transfer over, like in this case, for instance, here, using an F-type connector with a coax cable, 75 or 50 ohm, whatever. Well, in this case, probably 75. So today, let's shift over to this side. Okay, this side does the reverse, where we take a signal from the L-band modem, we take the modulator output and feed it into a block-up converter. And what that does, that takes the IF signal, which is an L-band signal, 950 to 1700 megahertz or to 2100 megahertz, and then moves it up to the allocation of the KU SATCOM signals, somewhere between 13 to 14 gigahertz. Okay. Now, if you try to survey these BUC devices, there's plenty of people that manufacture these devices. Some of them in North America, some in Europe, and some in the Asian, Japanese and Chinese. Okay, but simply they can vary in power from anywhere few watts to, like, say, 200 watts. Some that are forced air cooled, like you see here. These are well, although this one is a KA band, I'm sorry. This must have grabbed it by mistake. But so you can see some that are cooled by forced air, and some lower power ones, they're conduction heat taken care of. So basically, this devices usually they have a waveguide interface on one side, a rectangular waveguide, WR75, and on the other side they have either N-type or F connector. Okay. So today, let's take it as an example. Let's see how we go about designing one at the system level. Now, this is the stage where you're trying to design the architecture, align the signals, pick the components, and at the top level, without going into final discrete components, you design it and verify it using system design tools, such as the one I'm going to be using today, which is the Pathwave SystemVue from Azure Technologies. So here's the BUC up converter, okay, in this colored box here. We start out with an L-band modem indoor unit, okay, that puts out a cable which has a reference, 10 megahertz reference, and an IF modulated signal, okay? And sometimes DC, sometimes, okay? So it goes up to the unit, the feed unit. The feed unit in here has to somehow duplex both the IF and the 10 megahertz. So it splits off the 10 megahertz. That 10 megahertz gets amplified and filtered and cleaned from jitter or whatever, and then fed into a phase lock loop local oscillator that generates a carrier. That carrier, CW carrier, is used in conjunction with the IF to perform the block up converter. And what it is nothing but more than just mixing them in a mixer, picking the sideband, the upper sideband, doing filtering, and then a series of amplification, and then onward. And usually this thing here for several watts, 10 watts, is usually housed like this with a heat sink. The enclosure is heat sinked, and so the frequencies that we're dealing with 10 megahertz, the IF signal, which is 950 to 1700, sometimes at 2100. And then we have a local oscillator. And in my case today, I'm going to design, to simplify the design, the local oscillator is going to be running at 1/4 of the frequency that is usually needed to up convert to KU band, which is this band here, 13 to 14, with fractions on there. So the reason we do this is because there's plenty of S-band synthesizers, chips that we can use from TI, Texas Instruments, or from analog devices. And so we use these to generate the signal, and then it's at 1/4 of the frequency. So this one here, usually the local oscillator for this band is 12.8 gigahertz. So we divide that by 4, it's 3.2. And then in the up converter itself, we multiply it by 4 to generate 4 times that frequency, okay? So again, the frequency allocation of KU band communications, as you can see here, just to draft some rough specifications for the buck-up converter, we start out with the receive and transmit bands. The receive bands we covered previously in the other video. For the LMB, it's from 10.95, so somewhere close to 11 gigahertz to like 13 gigahertz. And then we have from 13 to 14 is the TX, okay? So here's the buck, here's the LMB, that's the receive side, transmit side. The local oscillator for buck is usually 12.8, okay? And of course, the IF is 950 megahertz to 1700. So here are some rough specifications for the system that we're going to be designing today, starting out with an IF signal, which is 950 to 2100 in the L band with a power level of 0 dBm. This comes from the modulator, okay? And then what we want to put that signal out at this frequency, okay? And at a power level which is greater than 10 watts. And utilizing the technology of GaN, gallium nitride amplifiers, okay? The reason for that is because it is the design is much simpler because the high power density of GaN devices compared to GAAs, we're going to end up with a small size and then lower number of devices to build up the power level to 10 watts. Okay, so let me, so here's the system that we have today, just to skip ahead to what we're going to be talking about. So I put up the system in here. So we're starting out with the satellite, the modem or modulator signal as being 0 dBm, okay, at the IF frequency. So we take that signal and then we have a duplexer that is from mini circuits with this part number. We'll show that in a minute, more details. That duplexes splits off the, it has one branch is a low pass filter that passes the 10 megahertz, and the other pass is what passes the IF signal, which is 950 to 1700 megahertz. So we don't need any amplification in here. We go straight. We use a filter, a ceramic filter, also from mini circuits, surface mount. These are all surface mount devices. And then we have a mixer from analog devices, a gas mixer, okay? And then we, of course, we have a local oscillator. We are synthesizing an S-band CW from a synthesizer, which uses that 10 megahertz. Okay, and then we multiply that 4 times. We have that at 0 dBm right now. We multiply it 4 times. And then we filter that, amplify and filter that signal, pad it down a little bit to offer a good return loss around the ports of the mixer. And that becomes 12.8 gigahertz. And then now the double sideband signal is here. Now we go through a few stages of amplification and filtering. So first we filter that signal to get rid of the lower sideband and the LO that leaks out of the mixer. And then we amplify first with a driver from, this one's for analog devices, gas, gallium arsenide chip. And then we filter the signal again and go into the final 10 watt GaN device, the GaN power amplifier, which is from the people at Corvo, okay? And then we have 2 utility pieces in here. One of them, this one here, is a 30 dB directional coupler. Well, actually, this is 40 dB directional coupler. And that's just nothing but a quarter wave edge-coupled microstrip printed coupler. And the reason for it is we couple the signal to go into a monitoring. We usually take this signal and detect it and sometimes measure the level, relative level, and display that to send that over to the computer or the microprocessor or microcontroller that is housed in the BUC as a controller for monitoring and protection. And then we have a ferrite isolator, and this one is a surface mount drop-in isolator. There's plenty of those that you can look at those. And we use those to have an isolation just in case if there's something happens to the waveguide that feeds the antenna system, just in case, so that if we get full reflection back, it will not damage the BUC. Especially this device here, that 10 watt GaN device, is somewhere between $300 and $500, the cost of that one alone, that device. So the devices, like I said, we're going to start out with this device here, surface mount duplexer from mini circuits, okay? That's this device here, which basically recovers the 10 megahertz that comes up on the feed line from the band modulator. And then we have a surface mount IF filter. This is the very same filter that I've used in my LMB, KU band LMB design that is previously a few videos back. You can check that video also, just so that you have complete picture of the KU band system. And of course, we have the mixer in here. It's a GaN mixer. It's a balanced mixer from Analog Devices. So this mixer is pretty good. This is a 13 dB LO mixer. Okay, so this is very good. That's why the LO needs to be taken care of as far as isolation from the RF port and the IF port, because it's very strong signal. And the reason we use this is because we want to have a very high third order intercept point, so we can drive as much as possible and get so that we can reduce the number of gains at the RF stages. We want to make sure that we drive in the IF level is most of the strength of the signal is magnified at the IF, not at the RF. They give you all the specifications. So basically, what I did is I grabbed these curves here and digitized them manually by hand and stored these values, for instance, for the conversion loss as a function of frequency, store those in the model, and you can see the model in here for this device. Okay, so basically come in here and you put in all the various parameters for that, okay? And of course, the circuit for this, let me see if they showed the recommended circuit use. Okay, there's nothing to it really. It's just basically in and out. So there's no other things than that. One thing I want to mention here is that we have this here, and these are, we utilize these inside the model, because we have M and N spurious outputs. And so in the LMB, I showed you how we can utilize this information in the model so that we can actually give all the spuriouses and images and so forth. And then we go into the, of course, the amplification part. And the first device, the driver, is this device here, which is a gas device, okay? And this device is straightforward. They give you all the info on this, and so it's pretty good. As you can see here, all you need is just basically to bypass the power supply and in and out. The DC blocks are internally to the device. And of course, you have VGG in here that you want to make sure you provide that. Then, of course, the humongous 10 watt or 25 watt in this case. That's one thing I forgot to mention. Even though I'm designing this system for 10 watts, but the device, the actual device is actually a 25 watt device. And of course, why would you say that? Because I want to back off the power level from saturation. As you know, the GaN devices, they have a very smooth, soft clip type of, so you can't really define 1 dB compression point because they start compressing early on. So you need to back them off really good to accommodate digital modulated signals. So this device, 25 watts, so I'm using it as a 10 watt device, but you could drive the whole thing. So it has a large signal gain of about, let's see, where is it? Large signal gain of 28 dB, okay? The device is here, okay, so, and the device, of course, you need to handle that carefully. You need to study the device and possibly get the evaluation board and fire that and run it. And one thing that so here's the usage of that device. So basically, we got the drain voltages on both sides, so you need to provide that along with the gate negative voltages, and there's a sequence of the biasing sequence. So make sure that that's why there's a microcontroller on this BUC design that takes care of the sequences. So you can't just turn off power, you'll damage the device. So there's a procedure to bias it up and bias it down, where you go into a sequence of events starting on. One thing you want to make sure of is that you purchase this evaluation board and experiment with it at first so that you don't have to keep blowing up these devices once you assemble them on your actual board. The other thing also I have done in the past is I would get this board, the DXF file. They provide you with this on their website. You can download the layout, the PC board, the artwork. So one thing you could do is you need to grab this and make sure you follow the exact layout, especially the thermal dissipation layout. Otherwise, the device will keep overheating and you won't get the efficiency that is claimed. Okay. So let's get back to the system. So let's look at, in general, let's look at some of the boards that I was able to see, find out on the that people published on BUC's KU band block up converters. Like for instance, this one here, and I think this may have been made in Japan because the actual devices that are used, I could see that they're all Japanese parts, Mitsumi and other ones, Toshiba. So like this is a system, and the other thing about this BUC example here, they've got the waveguide interfaces built in. The other ones actually it's sideways, and so these people in here, this is for both vertical and horizontal. And you could see that here's the waveguide, the strip line to waveguide, to rectangular waveguide interface on the vertical, and this is on the horizontal. But starting out way back at the IF comes in here using an F connector, and it goes in the DC. Of course, you extract DC. The DC in this design here, this is probably a 10 watt or 15 watt or 20 watts at most, I would say, unless it's really down in the 5-6 watts. Although there are two power amplifier gas fit devices. This is a previous generation. You might say this is like 10 years old. So the devices were used then is all gas fits, okay? And here's the mixer in here. So we have the IF that comes in here, DC goes out here, gets regulated and cleaned and distributed. And then there's an IF chain in here that takes care of the IF signal, comes up to this mixer here. The mixer now, there's a synthesizer on here that creates the local oscillator, and it filters it, amplifies it again, and then filter it. So the LO comes in here. This is a mixer. You go out, and there's a filter that gets rid of one of the side bands. And then the signal comes in here. Of course, in here, you have to create, in this case, it's they're sending the signal over two different polarizations. So they split off with a branch line 90-degree hybrid. Both, this is two double for broad bandwidth. So you can see one, this is the isolated port, 10 millimeter or 50 ohm. They split off, and then they go through two stages of amplification. Well, here's a driver, here's the final PA, and then they feed another quadrature here to combine the power from both sides, and then they split the power into two. One goes here and one goes here, okay? So you can see this is, when we use GaN amplifier, we can get rid of most of these devices into one. So this is probably, I would say this might have been somewhere between 10 to 20 watts, I would say. The part numbers are here. These are Japanese. You can look them up. I didn't have time to look those up, but you can look up those devices. Now, here's another example. Likewise here, this example here also, you can see that one polarization here, one polarization here. Or it could be actually they're both the same polarization but different. That's for redundancy probably. So again, in here, your signal comes out. So let's see where we start. We start right here. So we have this is probably the LO signal. This is the LO signal. Here's the LO band pass filter, and then we go out here. This is a mixer. You can see that's clearly the mixer in here. And then the IF is somewhere in here. All of that is an IF section with controller and all that. We go into the filter, an edge coupled filter, and then we have a whole chain of amplification and filtering up to this point here, where we have one of the filters in here, and we create a quadrature signal in here. So these are the two devices in here, somebody handwritten over them. And then, of course, we have the same exact type of network that we had in the other one. This is another device also. You can see clearly the same thing. So we've got the final PAs are here, and the quadrature output in here, combiner, the quadrature splitter in here, and this is the driver. This is final A PA device on one leg, and all of this is pre-driver filtering. This is the mixer in here. This is the local oscillator coming in here. This is the synthesizer on this side, and the IF is coming from this one. You can see clearly where that connector is. So IF comes in here. So it goes in here. This is the mixer. You mix. The DC comes out here, and this gets regulated in here, distributed. And this is probably a PIC microcontroller in here that runs the whole system. So back to my system now. So we're going to simplify this. So we know that we have 0 dBm from the L-band modulator. We want to take that into a duplexer to split off the 10 megahertz one way, and the IF another way, and then we're going to filter, pat it down, and then go into the mixer, mix with an SPS synthesizer at 1/4 of the frequencies. You can see here 3.2 gigahertz. We multiply that 4 times with this chip here from Analog Devices, and then we amplify and filter that, and then go into the mixer. We pad down and then filter, and then that's the driver. Filter again to suppress harmonics and other components. And then we go into the final GaN device, which is here. This is the 20-watt amplifier device. And then we go out through a direction coupler that samples the signal 40 dB below, that goes over to a monitoring section for protection and monitoring. And then to protect the whole system from reflections from the antenna feed, we put this circulator. And this is important, not just protection, because once you assemble this in the field, nothing can comes in there unless, of course, like a bird would land on the horn antenna, or somebody puts their hand, or the antenna collapses down from wind. If that doesn't happen, usually this also can protect you from when you're in the lab or testing in the production, so that if advertently somebody opens this or shorts it or somehow turn this system on while he's assembling the waveguide assembly part in here, or the power meter in here, that will protect you from reflection back that will damage the power amplifier. So starting out, so we designed, the first thing we designed is the local oscillator filter. That's a third order in here. So it's very simple, straightforward hairpin filter, okay, that we need the system. Once we pass that, we make a footprint of this, and the BCB, in the BCB, we bring this in, and this needs to be EM'd, and we need to do lid effect on it. So this is postponed until the layout is done. We do it in the layout. So at the beginning, we just synthesize it. In this case, it's synthesized using Genesis, a tool from Agilent also. The other filter we design is the bandpass filter on the for the upper sideband, the transmit filter. Okay. The IF filter, like I said, is basically provided. It's a surface mount chip, ceramic chip from many circuits. And here is the performance. I will show you in a minute on the simulator. So basically what we have here, these are this is the chain going from IF to RF. And this is these parameters that I have picked to display, where DCP is the desired channel power. There's C gain is a cumulative gain. C noise figure, NF is cumulative noise figure. IP 1 dB compression point, and then the compression value, the cumulative compression, okay? So we can see through the chain now how the gain, by the way, because I started at 0 dBm, the IF level from the L-band modem, it's overlapped with the gain because it's the fact it's 0 dBm. So the gain and the desired channel power are overlapped in this trace here. So you can see that we come in here, we have a little bit of losses in here, and then we go down to it goes down the mixer. Once it arrives the mixer, of course, you have the conversion loss. And then we have a little loss in here by this pad, and then we go further, and we hit the first amplification in here, hits this device here, which is 30 dB. We go up here, and then we filter, and then again, go up into the final PA device. We have the large signal gain in here, and then we have a tiny little loss from both the directional coupler and the isolator, and these are estimated about 0.6 dB. Now, if you trace the other parameters, they're all the same way. So basically, one thing good to monitor is this compression in here. So by the way, the GaN devices, usually they're most efficient when they're compressed like few dBs into compression. But in that case, of course, if you're doing digital communications, the EVM will be high. And so some people resort to pre-distortion, linearization type, whatever, but we chose to back this device. It's a 24-watt device. We chose to back it off. So the compression here, you can see this compression value is only 0.5 dB into compression here at this stage here, okay? Now, the noise figure is a little bit high. It's 22 dBs, and that's because in here, I chose not to use any amplifiers in the IF stage. So you've got all passive components. You've got the duplexer, the filter, the pad, the mixer, another pad, and then onto another filter. And up to this point is we start amplification and establishing noise figure, okay? So that's why when you look at this, there's about 20 dB of conversion loss in this stage here. And that's why the gain. But now, this is really fictitious because as soon as you put an amplifier, if you were to go back from the DAC that generates the IF signal, then obviously there you establish the noise figure, which will be more reasonably between say 5 and 10 dB. That's okay for a transmitter, okay? So the yellow part in here, we verified how it's working is by defining this path from here to the local oscillator port on the mixer, and this one was specified for 13 dBm, and that's where we get it for 13. Of course, beyond that, the signal just dies because we simply reject the yellow in here. That's what you see in here is tremendous amount of loss. On the system, I sweep the front end, and this is what you get. This is the power of the IF, the L band signal into the lockup converter. So you can see that we don't compress until we get to 6 dBms. And the optimal drive for this, of course, I'm driving with 0 dBm in here to obtain 40 dBm. So we're backed off by 6-7 dBs, which is typically that's close to the peak to average ratio of these digital modulated signals. So we're okay. This shows the overall frequency selectivity of the chain from IF to RF. So you can see it's nice. And of course, the output right now is 39.58 dBms. When this was captured, I may have aligned this, but now one of the good things that we do on the system is we can sweep the frequencies and look at all the various spectral components that are thought to will result. And so this is looking from 0 to 16 gigahertz. We're looking at all the systems, and we can see that we're getting, there's the DC, because I don't have any DC blocking on the mixer. At the system level, that's okay, of course. We're not talking about the next step of taking this design and going in down and start doing stuff in the ADS active devices. Then we have the IF leak in there at the output, okay? And then we have the actual desired signal in here. We have the image in here and a few other replicas of the image. We have also some in-band signal that are coming in here, and we can go into the tool and start analyzing where these are coming from and trying to minimize these, okay? So let's go back to the simulator, and this is a simulator, as I said before. So we come in here, we set up the linear analysis, and we set these paths, okay? And these paths, basically, we set them up so that we could look at the signal progression from IF in here to RF on this side, okay? And that's what we end up with. So we've got the, this is the frequency selectivity. At first, we can see that the signal is 40 dBm across, okay? The linearity of the front end, we can see how the system behaves as you drive from very low signals to saturation at 44 dBm, okay? This is the frequency response of the duplexer at the for the reference for the PLL, which is 10 megahertz, so it's very flat. Okay. This is the sweeping of images and spurious, and you can see that we can hover on this and find out what these components are. So these are all of these are related to the second harmonic of the IF signal interaction with the higher order, the M plus minus N, MRF plus minus NLO, and that's where all of these. And ideally, you want this one from here to be at least whatever in-band rejection ratio that you want. This is the image. It's pretty low down. So this is very good. So this is the progression of the gain and noise figure and compression and overall gain with the devices starting out from the duplexer all the way to the isolator. Okay. And of course the LO port as we come in. Okay, we start out from 0 dBm. We go into this side in here. Okay. This is the multiplier. It's an active multiplier, so it has an amplifier in it. Okay, so and then we have the little pad, and again we amplify in here, and then we have a filter and then a pad a little bit until we get to the mixer in here, and that's where it collapses. Okay, the filters that we're using, basically we've got here are these filters that were designed previously, and we look at them one by one. So this is this here is a duplexer. You can see the low, the 10 megahertz path, and then here is the IF path. So we can see that we start around 600 megahertz up, is where it becomes really flat and nice. So. Well, there you have it, ladies and gentlemen. So if you like this stuff, I have my usual training held for this kind of stuff and for the ANSYS HFSS. This training, I carry this training here in Jordan. If you're in the areas of the Gulf countries, Turkey, Egypt, North Africa, if you like to come into this training, I welcome you to reach out to me and so to host you on this training. And basically what we cover in here, you can go to my YouTube channel and you can see there the videos that we cover. Basically, we've got about 30 videos that we cover. We get to come in person and download an evaluation copy of HFSS and start building all of these devices that are in the videos in there. So the other training that I have is a two-part training on SystemVue, Pathwave SystemVue, basically system level baseband type simulations like I just showed you in the BUC. Now the next step for the LMB that I've done one video on and the BUC is to actually go back and attach a baseband section to it. So basically just to study the inner modulations, the spectral growth, and the PA efficiency of the system. So We'll do that in the coming videos. So you learn all of that in this training. The other training is where you go down further down in the hierarchy of building the system, is where you actually go in and start building stuff and figuring out how you're going to tune it, get all the DC levels in there, the large signal model, small signal model, analyze and basically come up with the real close to the final circuit schematics. And then beyond that, we have another training, which I did not include it in here, with where you go into Cadence and you use Allegro and OrCAD to do schematic capture and BCBLR. And that's where you take the artwork that comes from either HFSS or the Pathwave ADS, AutoPro, all the stuff that you take the pieces that you EM'd and you design based on EM that are sensitive to layout, and you take it in there. So if you like what you're seeing here, please reach out to me. I hold these sessions every 3 months. So I welcome you to reach out to me on this phone or this email. Well, ladies and gentlemen, this is Dr. Mohamed Nezami. I thank you again. Please shoot me an email if you have any concerns, any questions. Let me know what you think. And until next time, I say thank you very much. Have a good day, night, whatever it is where you are.